y'all? Darrelly Berry Jr. here, back for some more physics, some astrophysics today. Or, well, I guess general relativity is it? I would say it's mostly astrophysics, I guess. Um, Even though in anything that deals with the speed of light, it should be applicable. But of course, what goes near the speed of light is things that travel through space. So, sure, it's just astrophysics. So I'll be talking a little bit about that, some of the basics, some of the notation, and the notation conventions always seemed a bit weird to me. So this semester upcoming, I'll be taking a cosmology class, graduate level. So I'm seeing that we'll be doing a lot of relativity level stuff, general relativity. So I might have mentioned this before. Those who's been watching, basically, special relativity deals with things that's moving, approaching the speed of light, but in inertial reference frames where the velocity is consistent. And general relativity deals with things that also are not in inertial reference frames, as the speed changes or is angular motions or things like that, where basically there's curves going on, but in just a steady motion in a line that's approaching the speed of light. So those who've been watching, a few weeks ago we did some special relativity with things like neutrons or muons or whatever going through space, and muons from the sun going near the speed of light. But general relativity deals with curved space. So if you look at the screen, what I have there, that's actually an image of the Messier 87 black hole. So the idea is that the black hole has captured light. Light has gone to the black hole, been captured in the gravitational field. And my understanding is the light is actually going straight with the space around the black hole due to its large gravitational mass. The large curvature of space, straight is curved. So the light is going straight through this curved space that's massively curved around this black hole. So it's basically spiraling around the black hole, and that's what we're seeing there. So if you look at the left, and I believe the originators of this photo, I believe they actually got a Nobel Prize for this photo. I believe the one on the top left, or I guess the bottom left, is the very first photo of the black hole. And then they've been taking subsequent photos and we're looking at a time lapse of it. So you can see the link to this article there. I didn't really look at the article. I just glimpsed at it, but I noticed they have some cool pictures of the black hole. So I mostly wanted to get the picture from it, but you can see the link to the article if you want to see. And some of the updated technology, so you can see the image on the edge is more blurred. It's so just like how when you look at the images of the CMB, the cosmic microwave background, some of the older images are more blurred. I believe like Hobie is one of the older images, and it's not as granulated. But if you look at the more recent images, I believe like the Planck satellite is one of them. It's a lot more granulated to images. So I'm not sure if the middle one is a new image or just a computer simulation of what it looks like. But suffice it to say, with a higher resolution, you can see the actual rings that the light makes around the black hole, which is pretty cool. So that's simply sort of a general relativity type image that I picked, dealing with a large curvature of space. And what we'll do today, I'll actually look at metrics. So we'll look at metrics and look at how metrics change. Apparently metrics is a very big thing in general relativity. There's also a new type of notation. So Einstein, when he came up with relativity, he came up with his own way of noting things. So understanding the Einstein notation is actually very important to understand relativity, because you want to understand what's going on. Hey, what's going on, Riker? Awesome. Thanks for being here. Thanks for dropping a line. And let me know if you have any questions or comments, and I'll be happy to try to answer as I go along. We'll be talking about some relativity, notation, and after today, I mean, I'm still understanding it myself, so definitely want to be a pro, but it'll give you a better idea. So I know after going over everything that I'm going to cover today, I could understand everything a little bit better because the notation it's a beast. So, but it's not so bad once you get the hang of it. All right, so let's go ahead and get started. So I guess the first thing I'll do is just talk a little bit about the notation in general. So say general relativity. All right. So let's start with the Einstein notation. So when we're dealing with relativity, you're dealing with usually four vectors. So you might see something that looks like this. And whenever you see a Greek symbol, let me draw this a bit better. And I think I need to I'll just roll with it. About this, I was about to adjust my template a bit, but it's fine. When you see this notation like this Greek Greek symbols are usually space-time, which means that this symbol here, when you see that, it actually means XO, X1, X2, X3, which is really T, X, Y, Z, with the convention that time, at least time is by itself because C is identified or defined to be one. Like I said, it's caught up just as you replied. Hope you had a lovely Christmas. Yes, nice and chill. Hope you had a good Christmas as well. So I definitely don't celebrate as much as I did when I was a kid, but I still like the time of year. It's nice and peaceful. So there we go. So now another interesting thing about the notation is when you see a repeated index, it's a sum. So let's say I have, and actually it might be better just to actually go into the actual whatchamacallit, but still it'd be good to see this. Let me find a good example to indicate this convention, which can get confusing. So why don't we look at the actual vector that we'll look at in a moment. So if you have a vector, and let's say we have a vector with um, lower indices, and we're going to use a matrix to get that from a higher indices. We'll talk about what the higher and lower indices mean. It was actually confusing to me. But the way this works is another Einstein notation convention. And then Riker said, yes, you're using C as the speed of light. Yes. Very, very common notation, except this is not common to me that C is going to be defined as 1. So C is usually, 3 times e to the 8 meters per second. We're going to define C as 1 for the time being, which is unusual, but I guess it's usual when you go into graduate general relativity. I guess it simplifies things in a way that makes the complicated stuff we're actually doing more reasonable than to have to carry around the speed of light as well. All right, so let's say we have this. Now, if we look at this, we have two duplicated indices, J. So the way it works in Einstein notation is whenever you see repeated indices, that's going to be a sum. So this is really Vij, Vj, J equals 1 to 3. So another convention is when you see the Greek symbols, it's space-time. But when you see the, what do you call this, the Latin symbols, that's just space. So the Latin symbols is only space X, Y, Z, and you still have to sum over them whenever you see the duplicated indices. So that means that this notation here in Einstein notation and in relativity, what it actually means is GI X Vx plus GI Y Vy plus GI Z Vz. Weird, right? And that was a question. I thought that was a comment. Yes, but I did actually review it. So speed of light, we're going to define it as c, which means that whenever we see time, technically there should be a c there. If you looked at my previous videos when I did some of the special relativity stuff, you saw how we had like the gamma and the notation with the matrices, and we ended up with c, t, x, y, z. So we're doing pretty much the same thing, except we won't be carrying a c around. So it makes things a little bit simpler. But we will have to utilize this notation convention where whenever we see a duplicated indices, it means a sum, even if the sum is not there. So in other words, the sum is not there here, but because there's a duplicated indices, it actually means the sum, which means it actually means this. So you have to keep this in mind because I may forget to mention it later. And when I'm just doing the notation, but I'm going to try to remember to do things explicitly. In the case I do forget, and you see I just jump out with some long thing that, and it seems like I missed a lot of steps, is because you have to keep in mind that any duplicated indices is going to be a summation, right? So any duplicated indices is going to be a summation. So you have to keep that in mind. So I think that's the main things to keep in mind. That's what confused me the most. One, keeping in mind that if you see just the indices like this, it's really a full vector. So things end up being very compact. Whenever you see a duplicated indices, is always a sum. And the Greek symbols is for space time. The Latin symbols is just for space. And that should be that. And I think I might need a little bit more room on my prop. Give me a second. I'll try to give it a bit more, increase the size of the window so the resolution is better for y'all. But I notice I'm getting off a bit more than I mean to. So let me increase that a little bit. Give it a little bit more room. There we go. So it's not as large, but I want to make sure I'm not cutting off too much. All right, there we go. So let's go ahead and get started with the actual physics. So what I'm going to do is we're going to take a coordinate transformation, and I'll show you all an example with countervariant and covariant vectors in 2 dimensions. So we'll start with a Cartesian coordinate. You're going to do 2D to keep it simple. Oh, and yes, the coordinates, it is bizarre. So it took me a while to get, I'm still not used to it. It took me a while to understand it well enough to be able to actually work with it. But it is, I don't know. I guess when you get more involved in the general relativity, things get so complicated that it simplifies the notation and makes things easier in the end. So I'm pretty sure in the future I'm going to be very thankful for it. But what we're going to do is we're going to take XY coordinates and we're going to transform them into X prime and Y prime coordinates. And we're going to do that with a point in the Cartesian coordinate plane. So I'm going to choose the point to be 3, 1. And what we're going to do with this very simple example, we'll be able to see the transformations and how it happens in general relativity with Einstein notation. So in the future, we'll be able to take this simple example here and I'll be able to do a lot more complicated things, and you'll be able to follow it and see what's going on. So pay attention to this one today, and it'll make a lot more sense in the future. So this is flat Euclidean space. Now, one thing to keep in mind when you're dealing with flat Euclidean space, we have dx squared is dx squared plus dy squared. We're leaving off the dz squared because we're just dealing with 2 dimensions. And one thing to keep in mind is that this is geometry. This is just, if you have a vector in space, it is only so long. So the ds will be basically this distance here. And I guess you could say ds scaled by a certain, whatever the length is, but that's going to be invariant. No matter what coordinate system we use, that distance has to stay the same. Which when we're dealing with relativity, if you recall, we might have a different frame that's moving. Well, we might call this the S prime frame, but it's moving at a certain velocity. And in that frame, even though it's moving, whether it's, the distance of this thing is going to be the same, might adjust for relativity, but it won't change because the coordinate system is different. So if I take this this frame that's moving, and let's say I stop that frame so it's stationary momentarily, even though the coordinate system, the actual values for these things, the x prime and y prime, the numbers for these will be very different. The length of this vector will have to be the same. So that means that whatever coordinate transformation we do is going to have to keep that invariant. So all the stuff that we do in the details is to keep these things invariant between the x and the x prime and the y prime frames. The length of that vector has to be the same because the physical vector is going to be the same. All right. So what we're going to do is to give this transformation, we're going to say that x prime is equal to 2x and y prime is equal to y. So we're going to transfer from the x to the x prime, the y to the y prime. And this is basically the difference between these 2 frames. The x prime frame, or unit there, is 2 times the original frame. The y will keep the same. Now, it may seem like the metric is going to, like, when we normally think about this, we might think, okay, since x prime is 2 times x, everything in x prime is going to be a little bit smaller, right? Because it's bigger than the x frame, so it's going to take a smaller amount of x prime to equal the same. But it actually works a little bit different when you're dealing with relativity in the notation. So we'll see how the metric and one of the vectors is actually bigger and the other one is smaller. But bear with me, we'll see how this goes. We'll take it step by step. So what we're going to do first is we're going to get the x prime component. So we can see that's going to be 2 dx, and dy prime is going to be dy. And so if we want dx prime in terms of dx, is going to be dx equals 1/2 dx prime, and dy just is still dy prime. So we're putting this in terms of our dx's, in terms of our new system, our new coordinate system that we're going to be transferring everything to. Now, as an aside, so we can take a look and see what we're going to be doing in the future, if I have a vector, it's going to be vx, vy, and if we're looking at, let's say, the normal coordinate frame, like our normal coordinate frame, our original coordinate system, the vector looks like this. We have a metric. That's what G is a metric. And we have Vj. Remember that these are going to be summed over. So that means we have Gi. Let me make sure I put this in the, let's say, Gi1 V1 plus Gi2 V2. This is how I get the I1. And then we can say this is GJ1 V1 plus GJ2 V2. So if I was to take these separately, let's say that I equals X. So we have Vx equals Vxx. Vx plus Gxy Vy. And in our normal coordinate system, when we don't have any stretching or anything like that, the matrix is going to be just the identity matrix. It's going to be like this. And Gxx is here, Gxy, Gyx, and Gyy. So what this means is that we're going to have 1 here, Vx plus 0. So Vx. Vy is going to be the same thing. It's going to be Gyx plus Gyy. V X Vy. 0 plus 1 Vy. So this equals Vy. You notice here that I have the indices down here and the indices up here. And what this will mean, as we'll see in a little bit, is the down indices basically refers to the coordinate system. It refers to basically the length of the coordinate system relative to the other coordinate system. And the up indices refers to the physical dimensions in space. So this is called contravariant. The lower indices, and the upper indices is called covariant. So this is just how it looks in our normal coordinate system. I want you to get a look at that because it helped me to see it like this before doing the transform vector, and it'll make more sense. So I found that it make more sense to do it that way. So now what we're going to do is we're going to actually utilize the point. Actually, let me skip that aside. That was just one aside. Now let's go ahead and do the actual conversion to, so there's 2 things that happens here. We have the Jacobian, which is a conversion between coordinates. And we have the V, which is the metric Jacobian. Right? So the Jacobian is the conversion between coordinates. And the metric, let me make sure I give you the proper wording of it. It converts between I said it earlier as the upper and lower vectors. It converts between the ways that lengths and angles are measured. So we can use the Jacobian to convert between the coordinates of one frame and the other. And we could use the metric to convert between whether we're looking at the coordinate, the vector in the form of a coordinate, and the vector in the form of the physical distance in space. And our ironic thing is, if we take the vector in the coordinate sense and the vector in the physical distance in space, it actually gives us the invariant length of the vector. So in general relativity, this multiplication between the different types of vectors, the coordinate conversion and the actual physical distance, is equivalent to saying the magnitude of the vector is the square root of x squared plus y squared. And actually they do it squared. So this is the invariant length squared as it looks in general relativity. And the equivalent that we're familiar with in our coordinate system is taking the vector squared and squaring it. So we're familiar with x squared plus y squared equals r squared. We're familiar with that. The equivalent in special relativity is getting these two vectors, the contravariant vector and the covariant vector, and multiplying those things together, and we get an equivalent invariant length. So let me know if you have any questions about that. I know right now it's all symbolic and abstract, but understanding these things are key to understanding what's going to come up, right? The notation, the way the vectors work with this metric, and what the metric means and how it ends up being invariant no matter what coordinate system we utilize by second. Oh, and I realized I still have the text there. Let me remove this text real fast. All right, there we go. So let me know if you have any questions before we move on. I'll start writing in the next phase of this where we start actually getting the Jacobian. And Riker says, so the invariant length is dependent on the actual vector length. Exactly. That's a good way to put it. The invariant length is the vector length itself. So this vector length here is not going to change as a vector in space. It's just a vector. It's just a physical object. But if I was to, let's say, write in the x prime and y prime vector, it's a totally different vector thing, right? Let's say that the x prime and y prime looks like this. What that means is that in x and y, normally just regular x and y, we get 3, 1 out of that. But we're going to get something totally different out of the prime one, right? That same point in x prime and y prime, we don't know what that's going to be, and these steps here will help elucidate what that will be. But it will be something different. But we do know that the invariant length, the length of that vector is going to be the same. All I'm doing is just writing a red line on there instead of a black line. It's going to be the same length, except now it's going to be in the terms of x prime and y prime. That's going to be invariant. So all of this complicated stuff that we're doing so that we can get that vector in terms of x prime, y prime, but it has to be invariant because that physical object is not going to change. But as we progress, eventually, what we're going to be doing is the x prime, y prime is going to be looking at that object moving near the speed of light, curving around the black hole or something. And even in that reference frame, when I look back at Earth, I'm gonna, through the dilations and everything, we're gonna have to be able to measure the same event, and it starts to get complicated to measure that same event in those different frames. That's the idea behind it. Yes, it is mind blowing. Einstein was a genius. So basically, we like tiptoeing our way through the things that he did. All right. So first, let's look at the Jacobian. Right. This is the conversion between coordinates. So let me actually. This was one. Just kind of looked at the vectors there. So I kind of numbered the different steps we'll go through. So 2, we'll look at the Jacobian. All right. So the Jacobian works like this. If I'm going to convert the vector between these two coordinates, the Jacobian is one of the ways to do that. So we can say v prime, the vector prime, is going to equal the Jacobian times the old vector. So basically, I'm going to get the vector in new terms. Now, the Jacobian, if I was to put it abstractly, looks like this. Basically, we have a change in the prime frame relative to the change in the original frame. So again, we're looking at these two vector spaces. We want to be able to convert between these two to find out what that same vector length is going to be in the new coordinates. So I want to know how much the x prime changes. As I move along x prime, how much does it change relative to how x changes? When I figure that change out, alternate between the two coordinate systems and get that same invariant vector. So we're going to stick with our two vectors, right? 1 and 2. So we can say that this is 1. Let me make sure I use my proper notation. 1, 1. We have partial x prime, partial x no prime, 2, 1. We have partial x prime over partial. Naturally, let's go ahead and do 2 over partial x2 prime on the top and partial, and I might actually put an extra 2 there. Hold up, I'll correct this momentarily. Partial x2 prime, this should be a 1. 1, there we go. So this is what I had for, no, it looks ugly. I have partial x prime 1 over partial x1, partial x prime 2, so I'm right here, partial x prime 2 over partial x1, partial x prime 1 over partial x2, and then partial x prime 2 over partial x2, no prime there. So this is basically the Jacobian matrix, how it works. It's basically a bunch of partial derivatives. And this could be expanded into a 3-vector or a 4-vector. I'm gonna write this a bit neater. But that's what we're looking at. So let me know if you have any questions about this, because we're going to actually look at this vector a lot, this matrix a lot as we go through. This problem is a bit similar, a bit simple. So this matrix looks similar to the G matrix, the metric matrix, but it works pretty much the same as far as application and converting things. And the vector in our example is going to be basically V1 and V2, since we're in a 2-vector. Now, the interesting thing is, if I'm going to apply this, it'll look like this. So V prime I equals J I J and V J. So if you notice, both of these, the indices is up, because I'm not going from covariant to contravariant or anything. I'm just going from the same vector in X to the same vector in X prime and Y prime. And keep in mind that J I J is going to be partial X prime I over partial X J. So again, here I called I, 1, 1, 2, 1, 1, 2, 2, 2. All it is just that notation there. All right, so to make it a bit more explicit, I will say the Jacobian is going to be, and to give you a bit of a what do you call it, label or a legend to what we're doing here. It's going to look like this. And now 2 vectors, so now instead of actually using indices, I'll put the actual letters in. We have partial x prime over partial x, partial x prime over partial y prime over partial x, and partial y prime over partial y. So all I did was switch from the indices notation, where in this case I equals 1, j equals 2, or technically I guess you can say I cycles from 1 to 2, actually. And here I just actually plugged in the x and y for the 1 and 2, and let me know if this is unclear. This is very important, because it may seem like we're just writing a bunch of stuff, but when you actually, as we get farther along, all we're looking at is this, right? So when you come back in a few weeks from now, right, you'll be thankful for this, because all general relativity is. So let me let you know what I did, by the way. I knew I wanted to talk about relativity. So I started looking at relativity and I was like, I have no idea what these people are talking about. I have no idea. So now I backed up, was like, okay, let's go back to what they're talking about here. I'm like, okay, I have no idea what they're talking about. And I kept going back and back and back. And this is where I could start understanding stuff. So all of this notation here eventually is going to be just walls of this stuff. So you have to understand this stuff. Well, when you come back in a few weeks from now, you're going to be like, what the hell is this guy talking about? When you say partial, it's also known as a derivative. Yes, good point, Riker. But these are partial derivatives. So you can look at it this way. Let's go back to this. So when I look at this changes, let me be more precise. In the x-axis, this changed 3 times, right? But in the y-axis, this is going to change a different amount to get to that same spot, right? So if we understand how much the x changes versus how much the x prime changes, then I can actually make some kind of conversion factor to change from x to x prime. Cut to this page. Or was it here? This is all we're doing. We're saying, I want to know how much the x prime changes versus how much the x changes. That's this right here. But we notice that the y is in relation to y prime. But also, if we look at this, we have some y prime in relation to x, right? And we have some x prime in relation to y. So I need to know how much all of this changes in relation to everything else. And thus we have this. Right? Did I write that here? So this is how much the change in x prime. And actually, let me go to the one that's written out explicitly here. So here we have the change in x prime over change in x. We have the change in y prime over change in x. We have the change in x prime over change in y. And the change in y prime over change in y. Now, the reason for the partial is it's in that particular direction. So this is only the change in the x direction relative to the change in the x direction, and the change in the y prime direction and the change in the change. So it's only that little bitty partial change in a specific direction. And the reason why we change from the change, like the box triangle change, to the partial, because we go into infinitesimal changes. So you want to know how it changes even a little bit, so we can be very precise and accurate. So all of this stuff is built upon Newtonian's things, ironically. So it builds upon Newtonian and then extends that to these very delicate changes and things. So now let's look at what we did before, right? Before we knew, or we decided that our change metric is this. So let's bring this down. We're going to see how this works a little bit. This was my x prime. This was my y prime. What that means that what we have is a matrix that is partial x of 2x, partial y of 2x, partial x of y, partial y of y. See how that works? So all I did was take this partial derivative and substitute in what my x prime was in my new coordinate system. X prime is 2x in my new coordinate system. So I'll plug that in. Plug that in, plug that in, plug that in. So now we have a partial derivative of x with respect to x of 2x. That's 2. Partial derivative with respect to y, and again, it's partial because it's only in that y direction, there's nothing. Partial derivative with respect to x of y is 0. And partial derivative of y with respect to y is 1. So now we have our Jacobian to change from these two coordinate systems is 2, 0, 0, 1. Right? So this is how we go from x, y to x prime, y prime. So we have that. Right? Now there's also a reverse Jacobian to go from x prime and y prime. And all we have to do to get that is flip these. So instead of x prime being on the top, x prime will be on the bottom, and then we'll get a matrix to go the other way, right? So you can do that as an exercise. You want to see how that works. It's basically the inverse of this matrix. So that they, and then we call the other matrix K, is going to be the identity matrix, which is to say that J times J inverse is going to be the identity matrix. So I'll leave that as an exercise if you'd like to do it. And do the same thing I just did here, but have the primes on the bottom, and you'll see that you get an inverse matrix. Okay, so we got the Jacobian. The other thing we'll need is the metric, right? Talked about the metric. And actually, first, let's go ahead and get the vectors. Let's use this Jacobian first. Let's do this first. All right. So what we'll do is we'll take the let me see. I did this several ways. Let me see the most straightforward way to do it to save on some time here. All right, let's just do it the direct way. So let's get this vector first in prime before we move on. So watch this notation here. Is going to be partial x prime over partial x mu and v mu. Right? So if I was to get my vx x prime, right? This will be, now, one thing I want you to notice is this is a duplicated indices, so that makes it a sum, right? So this is going to be partial x prime over partial x vx plus partial x prime over partial y vy. And it probably would have been better for me to label that as i's and j's, but you could bear with me there. So if we look at this, all we have to do is plug this stuff in. Our partial x over x is 2. So this is 2 vx plus, and the other one was 0 vy. And if we look at the vectors that we're working with, we pick the vector to be 3, 1. So this is vx and vy. So that means that I can plug in my vx here. This is 2, 3 plus 0, so that's 6. And if I did this same process with y prime, this is going to be partial y prime over partial x vx plus partial y prime over partial y vy. So this ends up being similarly 0 vx plus, this was 1 vy, and vy is 1 as we saw earlier, so this ends up being just 1. So this means that my vector in v prime, given the um, transformation that we chose is going to be 6, 1, right? And this is the contravariant vector. So again, in general relativity, this is the up one, and now we have to find the lower one, and we'll confirm that this ends up being the same length in Cartesian squared. Let me know if you have any questions so far. All right. So I'll start to move on to the third one, which is the metric that we'll be able to utilize to get the lower version. But again, let me know if you have any questions while I'll just write this out silently with the save set. And I'll look for any questions in the chat momentarily. So it looks like no questions on this part. So let's go to the metric. So we have this. We have one part of it. Then we're going to get the second part, which is the lower one. So now we're trying to get the lower one now. We need the metric to do that. So the way that works is to get the lower coordinate vector in the new coordinate system, we need the metric, and it looks like this. So we need the metric. We already have the vectors here. We have the upper vectors here. We need the metric to transform that. Now, there's multiple ways to do this. The most direct way is to simply insert this into the length element directly. So we know that we have this, right? Earlier, we did the conversion between these two. We'll do that earlier somewhere here. So I'm going to copy this down so you can see that we're utilizing the same thing that we did earlier. So everything we did here was, nothing was for naught. So if I plug this in those terms have 1/2 dx prime squared plus dy prime squared. So this becomes 1/4 dx prime squared plus dy prime squared. This actually gives us our metric, because the metric will look like this, as I mentioned earlier, similar to the Jacobian. So I'll call it gxy is going to be gxx, gxy, gyx, gyy. Again, similar to the way the Jacobian worked, where we had the xx, yx, xy, yy. The difference is just that it's sort of next to each other on the side instead of a vertical differential. And we can see the x squared one here, 1/4. There's no xy, there's no yx, and then we have 1. So this means that our metric to lower the coordinate from the covariant and contravariant vector to the covariant vector is simply this. Now let's see how this works by plugging this in, right? So some more notation. We have, and actually I did a extra thing where I converted it. You're able to actually get a metric in the prime version as well, but there's no need to do that. Let me go straight to, give me a moment. Let's see where I pick up at here. So I see I'm almost at the end of the hour. Let me make sure I get this vector part in the most direct way. And why don't we do, All right, here we go. This way should do it. All right, so we'll do v lower x prime equals g x k prime v prime k. So I'm going to note that this is a summed over indices. This is the same thing we did here, but slightly more explicitly. So I'm going to write it out as a sum. Let's say that a actually this would have been k. We have g x prime x v prime x plus g prime x y v prime y. Because again, this is the sum indices, so I'm writing it a little less explicitly, but you remember that from earlier. We have the g here is going to be 1/4, and prime for the up one is 6 plus, and well, that was 0, so we can alter that out. 6 times 1/4 is 1.5. Almost finished. We'll get to the prime y1. I'll write this out in the slightly more explicit notation that I did before. V prime L. And again, this is a duplicated indices, so that means that it's summed in Einstein notation. So that means I have G, Y, X, and V prime X plus G, Y, Y, V prime Y. We know that that's going to be 0 plus the G in that is 1. We know that the vector was 1 as well. It was 6, 1. So we're going to plug in a 1 there. Automatic light thing. Get this to come back on. So this equals 1. Right? So this means that our vector in the lowered prime is going to be 1.5 and 1. Right? All right, so now we have it. So now we could test this stuff out. We can test this stuff out and see if the Einstein vector jinky thingy works. And newsflash, I did it earlier, so I know it works. All right. So we have ds squared equals x squared plus y squared. So we know from earlier that's going to be 3 squared plus 1 squared. That equals 10. We got that earlier. So this is basically the length of the thing squared, right? So we did the magnitude of the vector squared. We know that's going to be the same thing. X squared plus y squared squared is going to be 9 plus 1, 10. That works out. So now let's try the Einstein thing. So we're going to have the upper times the lower, right? So that's going to be, and let me make sure I write it in the snazzy way I wrote it before. It's going to be 1.516, right? So we have 6 times 1.5 plus 1 times 1. So that equals 9 plus 1 equals 10. See how that works? So we have the differential element. And the normal Cartesian way we'll do the length of a vector gives us 10, the magnitude of 10. We got the contravariant vector in Einstein notation and the covariant vector in Einstein notation by utilizing the metric to convert between the two, the x and the x prime, the y and the y prime. We multiply those together. And again, this is more of the coordinate, the vector, the coordinate length. And this is more of the physical dimension. We multiply those two together as vectors. And what do we get? We see that in the new coordinate system, in the relativistic notation, the length of the vector is the same. I guess I should say the length squared. So this is all the length squared. So this is important because later, as we will see, when we start to include the speed of light and we start to do things in full vector space where we include time, the length itself is not necessarily the same. The square of it is the same because time makes it a lot more complicated. It just what happens here. It's because we're not including time anyway. It's all the same anyway. But when we get to including time more explicitly, we'll see that it's the length squared. So that's why I did the same thing here and kept it the length squared because that's the way it is. Squared. All right. So that's it for today. There's some general relativity. Got it done in an hour. Hopefully you all enjoyed. And I'll be back next week for some more general relativity, I'm sure. Probably do move on to more complicated stuff. So make sure you understand this stuff because again, it gets ugly when we start looking at the more in-depth cosmology stuff. Is there going to be walls of this stuff? And I'll be forgetting to mention sometimes that these indices sum and it'll look I'm just getting sums out of nowhere. And it'll look like I'm just getting all kind of crazy vectors out of nowhere, but really it's just this. We have to know that that's a vector because it's a Greek symbol. It gets crazy. But apparently, it's just as we start to get more in depth with it, it's easier to note all of this stuff when you have this compact notation. So I'm glad you were here, Riker. Thanks for dropping a line. I hope you enjoyed. Hope it was informative. And trust me, as you see in the future, all of this stuff will be much handiness when we start to look at more complicated stuff. And everybody else who watched, if you can drop a line. It's good seeing you pop up on the views. And I'll see you all next time.